Welcome. In this session, we'll solve the previous problem that we solved using the concept of complex roots, but this time we'll avoid that using that complex roots approach. Okay, this time we'll use a slightly different approach, means simply writing the solution, then finding the constants. All right. So what I'm saying, so we'll solve the same problem that we solved in the previous session. So let me write the problem first. So we have a resistor here. There is a voltage source here. And we have a switch here. And there is capacitor. Then we have an inductor here. And we have a resistor here. So this switch is opened at t equal to 0. And this is equal to 4 ohm. This is equal to 10 volt. This is 0.02 farad. This is 3 ohm. This is 0.5 Henry. And this is 6 ohm. And we have to find I of t. So our goal is to find I of t for t greater or equal to 0. All right. So what we do first, we find the initial conditions, or what is the condition just before the switching of this network. So in other words, we'll redraw the circuit at t equal to 0 minus. So just before the switching is denoted by t equal to 0 minus. So that means switch was closed, because what we are doing, the switch is getting opened at t equal to this 0. So just before the switching, switch was closed here. So what will happen to the network? As you can see, switch is closed. That means this was there for a long time. In other words, the network is in steady state. In other words, that means capacitor and inductors are fully charged in this network. So if these two are fully charged, capacitor will act as an open circuit, inductor will act as a short circuit. So capacitor will act as an open circuit, then there is resistor, and inductor will act as a short circuit. Then we have a star. So we'll write the values of, so the value of the capacitor voltage at t equal to 0 minus, and value of the inductor current at t equal to 0 minus, that is I of 0 minus. This is 3 ohm, this is 6 ohm, this is 4 ohm, and this is 10 volts. Now you can see, since this path is open, there will be no current going into this. So that, in other words, there is no drop in this 3 ohm resistor. When there is no drop in this 3 ohm resistor, that means V of 0 minus is directly across this 6 ohm resistor. So what is I of 0 minus? I of 0 minus, you can see, is the current flowing here. You can see it is the current going through this, right? So I of 0 minus is equal to 10 divided by 4 plus 6, which is equal to 10. So 10 by 10, that's equal to 1 ampere. So the initial value of the inductor current is 1 ampere. Same way, what is the value of V of 0 minus? It is equal to 6 multiplied by I of 0 minus, because this is the current that's flowing here. So it is 6 multiplied by 1, that's equal to 6 volts. So we have found the value of the initial value of the capacitor voltage and inductor voltage just before the switching. So if the value of the inductor current just before switching is 1 ampere, what's the value of the inductor current after the switching? Just after the switch, means at t equal to 0 plus. So at t equal to 0 plus, what is the value of inductor current? I of 0 plus will be equal to I of 0 minus, because inductor current cannot change suddenly. Same way, V of 0 plus will be equal to V of 0 minus. Capacitor voltage cannot change suddenly, right? So we have the initial value of these. So what we will do? So at for t greater or equal to 0, for t greater or equal to 0, or t greater than 0, now this switch is open here, right? So we'll redraw this network. The switch is open. So we have a capacitor, we have a resistor here, we have an inductor, and we have so this is for t greater or equal to 0. This is our network. So this is 10 volts. This is 4 ohm. As you can see, there is no fun of this 10 volt and 4 ohm series resistor. This is 0.02 farad. This is 3 ohm. This is 6 ohm, and this is 0.5 Henry or 1/2 Henry. This is I of t. Our goal is to find I of t. Okay, that's what we have to do in this. So what we'll do, you will use the Laplace transform approach to find the value of this I of t for t greater or equal to 0. So what we'll do, we'll find the value of this I of t. We'll find using the Laplace transform. So we'll replace this network by its Laplace transform version. Now we know if we have a capacitor and it has some initial voltage at t equal to 0, the equivalent circuit of the capacitor is simply, so if this is C, then the equivalent circuit of this capacitor in the Laplace transform domain will be simply one series impedance, that is 1 by SC, in series with V of 0 minus divided by S. Same way, if we have an inductor that has inductance L, then we can replace it by an impedance in series with a voltage. Okay, so this is the values of these quantities will be simply Ls, and this is I of 0 minus L times I of 0 minus L is the inductance. So drawing the equivalent model, and for resistor, it is replaced by the same impedance value. Same resistor is replaced by the same impedance value. So writing the equivalent circuit of this and avoiding this part here, okay, because this has no role in the circuit now. So to draw the equivalent circuit, we'll replace capacitor by an impedance in series with a voltage source. Now value of this voltage source we write is V0. V0 is 6, so 6 divided by S. Then there is in series resistor, and value of this 1 by SC here is simply 50 by S, because it will be 1 by CS. C is 0.02. 1 by 0.02 is 50. Then inductor will replace by an impedance LS. L is 1 by 2, so it will be S by 2 in series with a voltage source. And the value of this voltage source is simply 1 by 2. Why? Because it is L I0. I0 is 1, L is 1 by 2. 6 ohm, this is 6 ohm, and then we have I of S here, right? So this is I of S. I of S we have to find. So again, writing the KVL for this. So it will be 6 IS minus 6 by S plus 50 by S times I of, we are writing KVL. KVL means some of the voltage drops will be equal to 0. So it will be S by 2 times I of S minus 1 by 2 plus 6 I of is equal to 0. So simplifying the terms or arranging these terms here, we have 6 IS here. Sorry, it is 3 IS. Okay, it's not 6, this is 3. So this is 3. This is 3 ohm. So it will be 3 IS, 6 IS is 9 IS. So IS I will take outside. So it is 9, 50 by S plus S by 2 I of S. So this is minus 6 by S minus 1 by 2, that's equal to 0. So arranging these terms, so it will be 9 plus 100 plus S squared 2S, just cross multiplying the terms. So it will be minus 12 minus S divided by 2S. This is equal to 0. Again, cross multiplying these terms, so we'll get 18S plus 100 plus S square I of S divided by 2S. This I will take on the right hand side, so it will be S plus 12 divided by 2S. You can see 2S and 2S will get cancelled from here. So we'll say I of S is simply S by 12, 18S plus 100 plus S square. So this I can write as S plus 12 S square plus 18S plus 100. Okay, so this is our I of S. Now to find the partial fraction expansion, what we have to do, we have to find the roots of this, right? We have already done this in the previous session, so we know S square plus 18S plus 100 can be written as S plus 9 minus 4.36J, and this will be S plus 9 plus 4.36J. This is, we have already done this in the, right? So this equation has complex roots. Okay. Now, if you know this part, means if the roots are complex and you know that, we can write the solution directly here. We don't need to find the value of A1, A2 if we use partial fraction expansion, right? If we do the partial fraction expression, what we have to write? S plus 9 minus 4.36J plus A2 divided by S plus 9 plus 4.36J, right? So if we use partial fraction expansion, we can find the value of A1 and A2 and then write the inverse Laplace transform. That's what we did in the previous class. But this time, remember, if you have a quadratic term, S square plus some K times S plus B. Now this, if you are able to express S plus alpha minus beta J or J beta. So we'll say J beta and S plus alpha plus beta J, right? So if you have this, then you can write the solution for this term. For this term, you can write this is simply equal to inverse, in other words, inverse Laplace transform. You can write it simply e to the power of minus alpha t A1 cos of r. Let me write A instead of A1, so not confused with this A1 here. A cos of beta t plus B sine of beta t. Okay, here alpha is 9, beta is 4.36. Okay, here alpha is 9, beta is 4.36. All right, so this is alpha and beta. So this is our I of t if we have terms like this. All right, so if you compare it this with this, you have alpha equal to 9, beta equal to 4.36. You can check. So in other words, we can write I of t simply as e to the power of alpha. Instead of alpha, we have 9. A, we don't know what's the value of A. Beta is 4.360 plus B sine beta is again 4.360. Now we don't know what's the value of A and B. Now, how do we get the value of A and B? We use initial conditions. So to get the value of A and B, what's wrong with my marker? Get the value of A and B, we use initial conditions. We use initial values of the voltage and currents. Now, we know the value of I of 0. What's the value of I of 0? It's equal to 1. We already found that from this here. Right? I of 0 is 1 here. We know the value of A of 0 here. That's what we will use here to find the value of this. Okay. So I of 0 is equal to 1. So put t equal to 0 here. So we'll say I of 0 is equal to e to the power of 0. E to the power of 0 is 1. Then A1 cos 0 is simply 1 plus B sine 0 is 0. So A1 is equal to I of 0. I of 0 is 1. So that this implies A1 is simply 1. So we have found the value. Sorry, not A1. This is A. Confusing the constant. So A is simply 1 here. So A we have found. Now we need to find the value of B. Now how do we find the value of B? What we'll do? To find the value of this here. So what we'll do? We'll say the voltage here, right? We have named it V. What is this voltage equal to here? So let me write it here. So we'll say, writing the KVL. So you know current will flow like this. So it will be 3 times I of t. What's wrong with my marker here? So it is 3 times I of t. So plus v, we don't know what's v, so let's keep it v of t, right? So let's keep it here. So it is in 0.5. Now the voltage across the inductor is written as di by dt plus 6I of t is equal to 0. Okay, so this is the KVL across the slope. Now put t equal to 0. So if you put t equal to 0, we have I of 0 plus v of 0 plus 0.5 di 0 by dt plus 6 times I of 0. Let me check what's wrong with my marker. Okay, so now we know the value of I of 0, we know the value of v of 0, we know the value of I of 0. So it is 3, I of 0 is 1, plus v of 0 is 6, plus 0.5 di 0 by dt, plus 6 times I of 0 is 1. So that's equal to 0. 3 plus 6 is 9, plus 6 is how much? Have I done it correct? I think this is wrong here. This is minus v, okay? This is minus v. Okay, this is minus v. This is wrong here. So this is minus v, okay? Right, so this is minus v, because when we write the KVL, it will be current is entering this way. So this terminal is plus, this terminal is minus, okay? That's why this is minus. So it is 3 plus 6 is 9 minus 6 plus 0.5 di t by dt. di 0 by dt is equal to 0. And we don't know the value of di 0 by dt. So this will be 3 plus 0.5 di 0 by dt. This is equal to 0. That means di 0 by dt is equal to 3 minus 3 divided by 0.5. That's equal to minus 6 amperes per second. So what is the value of di 0 by dt? Now you know I of t already here. We have already determined the value of I of t. So differentiate it with respect to t. So if you differentiate this expression, what we'll get? So differentiating this expression with respect to t. So we'll say di by dt is equal to, first we'll differentiate this term, then we'll differentiate, because this is differentiation of u and v. So product rule will apply. So it will be e to the power of minus 9t, and differentiation of e to the power of minus 9t is minus 9. Okay, a cos 4.360 plus b sine 4.36t. Okay, so 4.36t plus now the differentiation of second term. So it is e to the power of minus 9t, and differentiation of second term will be minus a times 4.36, because differentiation of cos 4.36 is minus 4.36 sine 4.63t plus 4.36b sine differentiation of sine is cos. Okay, let me rewrite this term. It's okay to avoid the confusion. So you have to differentiate now the second term. That is a cos 4.36t plus b sine 4.6t. So the differentiation of this term is simply differentiation of cos is sine. So it is a sine minus sine. Okay, it is minus sine 4.36t multiplied by this will come out. So in the product 4.36 plus b differentiation of sine is cos 4.36t, and this will come out. So it is 4.360. So this is di by dt. Now put t equal to 0 here. So when you put t equal to 0, di by dt is equal to e to the power of 0 is again 1. So it will be simply minus 9, and it will be a1 a cos 0 is 1 plus this term will be 0, right? So e to the power of 0 is again 1. So e to the power of 0 is 1 multiplied by minus this term will be 0 because sine 0 is 0. So 0 plus b cos 0 is 1, 4.36. Okay, this is not t here. Okay, 4.36. So this is our di by dt. But what's our di by dt here? It is minus 6. So substituting the value of minus 6 here. So it will be minus 6. That's equal to minus 9 times a plus 4.36b. Okay. Now what's a? We have already found this is equal to 1. So that means it will be minus 6 equal to minus 9 times 1 plus 4.36b. So b will be equal to minus 6 plus 9 divided by 4.36. Right, so that's equal to 3 divided by 4.36. I think that's equal to 0.688. Now substituting the value of a and b here, we can write the current here. So that means I of t is simply e to the power of minus 9t. A is simply 1, so it is cos 4.36t plus b is 0.688 sine 4.36t. Okay, so what we have done in this approach, let me repeat this. What we did, we wrote the solution directly. If we have the complex roots of the quadratic term, we can write the solution for this quadratic term directly. We can use this method. We can write the solution directly. If the roots are alpha minus b zeta or alpha plus g beta, then we can write the solution directly. So we don't need to first find the a1 and a2, then write the solution. So we can write the solution directly. You can check the solution will be. Then there are two unknown constants. That's a and b here. How do we evaluate a and b? A and b you evaluate from the initial conditions. And from the first initial condition, when we put I of 0 equal to 0, we get a here. Okay. Then to use v minus value of 0, we wrote the KVL equation. So when we wrote the KVL equation, one quantity arises here, that is di by dt. So how do I determine di by dt? I know I, so I can differentiate it. So we know I of t is e to the power of minus 9 a cos 4.36t plus b sin 4. So differentiate it. Now this is a product term. We have the product of two terms, so you will use the product rule of differentiation. And then finally put t equal to 0. You will say di 0 by dt is something like this. Now substituting the values of the quantities, you will get b. And this is the solution. Now compare the solution, this solution that we already found in the previous class, if you remember. So this is the solution what we have, e to the power of minus 9t for cos of 4.36t plus 0.688 sine of. Now compare it with the session we have already done in the previous class. You can check where we found the residues first. In the previous class, we found the residues, then wrote the solution. You can see the solution is identical. Okay, the solution is identical. The solution is simply same, right? So either you use if you know the complex algebra, you can use that, or you can use the initial condition approach. You will get the same answer. The answer will be same. Okay, let me leave this session here.